Alrighty, folks, so you made it to the end of lesson number 1. Congratulations, this is the last video. So now we're going to talk about the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic states that every integer n except 0 and plus and minus 1 is a product of primes. So we've already shown that we could write anyone as a product of primes. We didn't prove it, but again, you could work on that if you really want to. So this prime factorization, so what we're stating here is we're stating that this prime factorization is unique in the following sense. So if I can write n as a product of some prime, so p1, p2, all the way up to pr, and I could also write n as a product of primes, say q1, q2, all the way up to qs, with each pi and qi or qj prime, then what has to be true? What has to be true is r has to equal s. So the number of primes has to be exactly the same. And after reordering and relabeling some of the q's, I can rewrite each of my pi's as plus or minus some qi's. So we're basically saying the decomposition is exactly the same. The order might be slightly differently written, but again, the primes that are used are going to be exactly the same. They might differ in the sense that there might be some negatives in there versus some positives beforehand, but again, the um, the overall sign of it, so whether or not it's positive or negative, will still remain the same. So if, say, P1 was positive, I could have Q1 and Q2 both being negative, and that negative negative would then make a positive, and everything would work out in the end. So basically what we're saying is everything is unique up to this reordering and relabeling in terms of the plus or minus. Now a corollary of this is if n is greater than 1, so every integer with n greater than 1 can be written in one and only one way in the following form. So if we set up this specific ordering, then everything is going to be unique to this. So where the pi's are positive primes such that p1 is less than or equal to p2 such that less than or equal all the way up to pr. So if we order them in this way, perfect. So for the last theorem, again, let n be greater than 1. If n has no positive prime factors less than or equal to the square root of n, then n is prime. So this theorem here gives us a test to be able to determine when something is a prime and when something is not a prime. So we know we can decompose any number. In this case, we're specifically stating that n is greater than 1, but the original idea is we could decompose everything that's not 0 or plus or minus 1, so this is meeting that condition. So we can decompose it into a product of primes. So this is just simply stating that in order for me to check that if n is a prime itself, if it can't be decomposed because it is a prime in itself, then we only need to check if it has prime factors up to the square root of n. So I don't need to check all of them, I just need to check all the primes up to the square root of n. So let's see this in action. We want to verify that 2 to the 5 minus 1 is in fact a prime. So exercise 7. So 2 to the 5 minus 1, well, this is equal to 2 to the 5 is 32, minus 1 gives me 31. So we want to ask, is 31 a prime? Well, it is a prime. Let's pretend we didn't know it was a prime. So the question is, can I decompose this as a product of primes? So remember before when I had that 1 billion and change, what I was doing is I was dividing out 2's and 3's, but I was dividing out primes. So there came a point in time where, if I hit 3, the next prime was 11. So I'd be missing everything that was in between. So the 5, the 7. So what ones do we need to check? Well, that last theorem simply said I don't need to check all of them up into 31. I just need to know, well, what's the square root of 31? Well, this is strictly less than 6. So I need to check all primes up to, but not including 6. So the primes up to 6 are 2, 3, and 5. So if 31 is a prime, then I shouldn't be able to divide out a 2, a 3, or a 5. Now we clearly see that 31 is not even, so 2 does not divide 31. What about 3? Well, 3 does not divide 31 either. Again, we can check that on the calculator. If you plugged in 31 divided by 3, you're going to end up with 10.33 and change. It doesn't divide perfectly. So 3 also does not divide 31. And lastly, well, 5 clearly doesn't divide 31. So based upon that last theorem, I don't need to check anything else. I've checked those 3 values, so all up to the square root of 31. None of them divide, so they're not prime factors. Therefore, 31 is prime. Alrighty, folks, so that is it for lesson number 1. Again, this is really just a review of things that we can do with the integers. So we've talked about divisibility. We've talked about the division algorithm. So how I can decompose a number into a product of two things plus a sum. When that remainder is 0, then I have something about divisibility. We have the greatest common divisor. And then from there, we started talking about primes and how we can decompose numbers into products of primes. So moving on, we're going to get into lesson number 2. We're going to be talking again in terms of arithmetic, but now we're going to deal with modular arithmetic. So everything when I was talking about mod something, we're going to get into that into the next lesson. So we'll see you then.